Manacher's algorithm is an efficient algorithm to find all palindromic substrings in a given string. The naive approach checks every possible center and expands around it to find palindromes. Since there are n centers and each expansion can take up to O(n) time complexity of the naive approach is O(n) squared. Before introducing Manacher's algorithm, you may notice so far we've been only talking about palindromes that have odd length. To also find even-length palindromes, we do a trick that converts even-length palindromes to odd length. This is done by inserting a special separator between every character. Here we use a hashtag, for example. Now, even-length palindromes in the original string are now odd-length palindromes that's centered around a hashtag. Because of this trick, for the rest of this video, we'll only talk about odd-length palindromes for simplification. Manacher's algorithm is able to find all palindromic substrings in O(n) time. The key optimization is that if the current center lies inside an already known palindrome, we can use the palindrome radius at its mirror position in that palindrome to skip part of the expansion. Let's look at this example. When expanding character B at index 3, we found a palindrome starting from index 0 to index 6. It's marked by two blue indicators L and R, and its center is marked by green indicator C. Now we're trying to expand around character A at index 4. We first find the mirrored position of it around C, which is index 2, marked by purple indicator. Because of the symmetric property of palindromes marked by L and R, within the range of L and R, center and mirror index are able to expand by the same amount. Here we're emphasizing within the range of L and R, because it's possible that the mirror can expand to the left of L, and the out-of-bound amount can't be used on the current center index. In this example, the palindrome radius at mirror position is 2, and this expands exactly to L, not out of L. So two characters can be skipped when we expand the current center, and comparison starts from the third character. We're able to expand another character but encounter a mismatch at second expansion. In Manacher's algorithm, we actually use L and R to record the palindrome with the most far-away right bound. Notice this palindrome is not necessarily the longest one. Just now, we found a new farthest palindrome, starting at 1 and ending at 7. We update L and R accordingly. Continue with the example. We now try to expand index 5. Its mirror position is index 3. Although its mirror position can expand 3 characters, only 2 are within the range of L and R. So in this case, we can only skip 2 characters, as the third character is outside the range that we know are symmetric. Now, let's look at the code. We keep track of the rightmost palindrome using 2 variables, C and R, for center and right bound. Notice that here L is actually not needed. C and R are enough. Next to the definitions, we still have a for loop for all center indexes. Inside each loop iteration, there are 3 parts. If center is inside the current rightmost palindrome, we find the mirror position and figure out how many characters we can skip. After that initial assignment, we try to expand further. The while loop checks the next characters just outside the current palindrome. While they match, increase the radius by 1. If the expanded palindrome is the new rightmost palindrome, we update accordingly. Let's run the code through an example. Let's analyze the time and space complexity. For time complexity, the main concern is the while loop that expands palindromes. At first glance, it looks like the while loop could run at most n squared times in total. But the key observation is, while loop runs only for expansions outside R, so every successful expansion increases R by 1. Since R never decreases and can increase at most n times. The total number of expansions across the whole algorithm is at most n. So overall, the algorithm runs in O(n) time. For space complexity, we need an array of size n to store radius value at each center. So the space complexity is O(n),